I'm going to largely focus on the first half of the deck, and then later on in the agenda, when we get into some of the design issues, Dana is going to jump in and take the second half. Just to give you a little bit of background, I work for NEEP, Northeast Energy Efficiency Partnerships. We're based just down the street in Lexington, Mass. We're a regional energy efficiency organization. Has been really promoting energy efficiency for over 20 years now. Air source heat pumps is a technology that we sort of adopted and recognized a number of years ago, five or 6 years ago, as a really exciting emerging technology. And a lot of the way that we do our work is around bringing together all kinds of stakeholders in the market from around the region and identifying barriers to the market and really trying to, again, work with a lot of different stakeholders to drive adoption of these exciting technologies. And I'll say that this is really, speaking of exciting, a really exciting time in the world of heat pumps and air source, and obviously we're talking about air source in this session. Tremendous recognition that this is a technology that can be a real game-changing solution for buildings, particularly as we look at decarbonizing our buildings over the next decade or two. This session is really kind of a foundational session. Try to give you guys some information just about what heat pumps are, their role in the market, their position as a solution as far as decarbonization goes. Dana's going to pick up the pieces on sort of best practice of design, installation, and operation. That's a really very important piece to this puzzle. The heat pump itself is very important, but getting it installed and operating in a certain way is very important as well. And we're here today with a lot of stakeholders, mainly from the new construction perspective. So hoping to really hope to tailor some of this information to you all so that you can really start to deploy this technology in your projects. So first and foremost, heat pumps have been around for a long time. And I think this is one of the challenges that we face is that the reputation of heat pumps, particularly in colder climates like Massachusetts, has not been great in terms of performance and reputation. They'd say that we're sort of this latest generation of technology is really seen drastic improvements in performance. And so one key takeaway that we always try to leave people with is that we're not talking about last generation heat pumps. We're really talking about it's in fundamental ways a new technology that really again is a very practical solution for the kinds of applications that we're looking to install them. The other piece is that this is a technology that in other parts of the world is the primary way that heating and cooling is going on. We have a lot of existing momentum in our state and in our country around fossil-based boilers and furnaces. So there is a lot of market intelligence that we can, and we're still trying to bring to our country as far as where to install these, how to install these, and really how to change the mindset of the broader market to really instill that kind of confidence that this is a really superior technology. A couple of the recent advances that have really made this technology kind of that next generation has really been some of the inverter-based drives and motors that are going into these systems. So instead of a traditional or older style system, I mean they're installed today, but mainly single and two speed that would either be on and then off, kind of trigger that cycling pattern, which is very inefficient. This allows the systems to modulate so they can go down to part loads, find a really comfortable lower capacity operation, and just hum along. And so it's instead of that on and off kind of situation, it allows these systems to provide heat, cool, and on a much more continuous basis at a much more efficient level as well. And with some of these other technologies in terms of the refrigerant changes and some of the heat exchangers, we're seeing systems that have better and better performance at lower temperatures. And this has obviously been really exciting as outdoor temperatures drop here in our region. The need obviously for heating capacity goes up. So the ability for this technology to maintain output capacity is very, very important, and we're seeing that in more and more systems today. So how do air source heat pumps work? And I'm going to invite Dana up in a moment, but I just wanted to compare sort of the traditional combustion of fuels to this sort of transfer of heat. And I'll start there, and I'll let Dana come up for a few quick words on this.
Yeah, so I'll just keep this pretty brief. I know, in growing up, sometimes refrigeration was one of those topics that was kind of passed over really quickly as you went through physics class, and, it's when everybody went to sleep. I certainly fell asleep every time I saw this, and what we're really dealing with is a refrigeration cycle that's been, improved upon some of the technological improvements that Dave mentioned with variable speed capacity, compressors, but the refrigerant that's used in these systems right now has a boiling point of negative 50 degrees Fahrenheit. That's really a key part of the advancement in the technology and why they can make these cold climate units. So what happens in these units is you have this refrigerant flowing through the system, circulating through, this is just showing like one line, but it's really two refrigerant lines circulating from the outdoor unit to the inside unit and back, circulating refrigerant to and fro. And when it comes to the outside unit during heating season, it goes through a low pressure valve. And when that refrigerant gets squirted through that low pressure valve, it has a very similar phenomenon to when you take a can of whipped cream and you spray it and the can gets cold. There's a change in the pressure. It goes into a low pressure state. It goes for it's diving for its boiling point of negative 50 degrees, which is significantly colder than anything that we're going to see outside, thankfully, hopefully, around here especially. And so that heat energy that's in the air all the time. So there is heat energy, and a lot of times people think of heat energy in terms of waves. You can feel it or you sense it coming across the room. But if you think of heat energy in terms of packets of energy, the same way you would with photons, it's called something called phonons. And so these heat particles are embedded in everything above absolute zero, which is, negative 273 degrees centigrade sort of thing. So even when it's very cold outside, 0 degrees, negative 10 degrees, there's still a lot of heat energy floating around, all these little heat particles. Well, so heat moves from anything that's warmer to stuff that's colder. So when the Freon is diving for negative 50 degrees and it's 0 degrees outside, all the heat energy that's flowing through the fan clings to the fan coil, gets absorbed into the refrigerant, and the refrigerant warms up to sort of outdoor ambient temperature, maybe around 0 degrees. So then when it goes into the compressor, that compressor takes the volume of refrigerant that enters into it and compresses it. It goes from 100 pounds per square inch, PSI, to something like 400 pounds. And when it does that, not only does the pressure go up, but you're compressing all of that heat energy. You have a higher density of heat particles inside of that refrigerant for that volume. And the physical manifestation of that is a higher temperature. So when it comes out of the compressor, now that refrigerant, instead of being at 0 degrees Fahrenheit, is at like 150 degrees Fahrenheit. Well, that's pretty hot. So then that flows through the copper line into the house, into a glorified radiator inside with a fan, and it blows that glorious heat into the house, moving that heat in. So then the refrigerant's more like room temperature. It flows back out to the outdoor unit at roughly room temperature and goes through the whole process again of expansion and contraction. It's almost like taking a sponge and clearing the water off of the counter, squeezing it into the sink. The heat energy goes into the sink, and then you can go back and you can scoop up some more and do it. And the efficiencies of these systems is that in order to move that refrigerant, all you have to do is run highly efficient motors, the fan and the compressor, and you're moving all that heat energy. So it's easier to move heat energy when it's warmer outside, because there's more heat energy, it's easier to scoop up. But when it gets really cold, the high-performance units are able to scroll up the compressors to very high speeds to move that refrigerant back and forth. They take the little scoops of energy and throw it into the house very quickly and continue to do that efficiently. So there's my refrigeration spiel. Nobody fell asleep. So there we go.
So costs, this is obviously a big question that a lot of people have in terms of how much it costs to install these kinds of systems. This is a bunch of data that was pulled together to look across these different kinds of systems. I'd say the bottom line is that both the ductless systems, and this is assuming a 25 square foot home and not necessarily high performance. So there's definitely some variable there that goes into the calculation here. You'll see that in many cases we're really at very much cost parity when it comes to installing ductless or essentially ducted systems with traditional oil, gas boilers and furnaces. Certainly there are a number of factors that are going to impact the math going forward as far as fuel prices. Obviously in our region we have a lot of fuel oil, so costs of existing oil boilers and furnaces, that the cost to deliver that heat going forward certainly could fluctuate quite a bit. Gas prices have been a lot more stable than oil, but certainly there could be some fluctuations there. There's certainly costs associated with bringing gas to two locations that shouldn't be, that should really be brought into discussion when you're thinking about the whole home and bringing the fuel to the home. This can be a significant cost. Certainly, there are a number of rebates. We'll talk about those and their effect on the economics of adopting these technologies. The heating load itself is obviously a big variable here when it comes to the cost of systems. The larger the load, the more the larger of a mechanical system you're likely going to need. So as we're talking about high performance homes, you bring the heat load down. The costs that were in the previous slide are likely to scale down as well. We get into a little bit later on in terms of some of the different configurations of heat pumps that we're seeing today. This slide hits on the fact that the heat pump bringing heat into the home can be distributed throughout the home in a lot of different ways, and they certainly will have impacts on the costs. Whether you're doing sort of an air-to-water system where you're using hydronic loops to distribute the heat throughout the home, or you're using whole home ductwork, or you're using more smaller ductless systems, that is certainly going to have a cost impact on the home, and we'll talk a little bit about that later. And obviously, a lot of the discussion, certainly from our perspective, is the benefits around the carbon impacts of delivering this heat to your home. And certainly this picture will change as the mix on the grid changes, but this is a snapshot with even today's mix. You're seeing dramatic savings on the greenhouse gas side from heating with heat pumps versus heating with traditional fossil fuels. And certainly, as I mentioned, that is likely to shift over the next, constantly. The grid is getting cleaner and cleaner, and so a quick early recap. The costs, we're at a point today that the air source heat pump technology is very competitive and very comparable to gas, even in this day and age where we have very, very cheap gas. A huge opportunity for this technology to be a carbon reducer today, and then obviously going forward in the future even more. Certainly can be emissions free. The ability to match either on-site or off-site renewables with air source heat pumps and creating a technology that can basically heat and cool with emissions free. And it's been hit on a number of times this morning. I mean, this need for Massachusetts, the region, the world to address climate change is certainly an urgent issue, and this is a pretty exciting way to help us move in that direction. I'm going to do a little bit on the economic. We're going to come back to the economics a little bit, get into the technologies a little bit, and then I'll hand it off to Dana. So we have a pretty robust incentive landscape here in Massachusetts, whether we're talking about the alternative energy certificates or Mass CEC's whole home air source heat pump pilot program, and now Mass Save's new home construction program. You'll see, we're really a number of ways to tap into incentives to help reduce the installed costs. I'm not going to get into all the details. I think we have representatives actually from all of these areas. I know we have a booth in the back specifically about alternative energy credits. I saw Meg Howard running around and Amy from Mass CEC that could probably speak to some of the details of the whole home program. And then, so the opportunity, talk a little bit about this opportunity to match air source heat pump and solar PV. As I mentioned before, when you have a clean clean source on your roof, powering an electric-based heating and cooling system, you're essentially doing that zero emissions for a lot of reasons. Super sustainable. This is a way to improve HERS scores as well. Just to highlight sort of, and for folks that were in the earlier session talking about the way that the solar market has changed in the last 5 to 10 years, really dramatic decreases in the cost of PV, and really makes this kind of combination very compelling, both on the retrofit side, but particularly on the new construction side. Of the opportunities for matching this with new construction. You see a couple of different comparisons between new construction, sort of an average building on the far right, new construction with obviously a smaller load in the middle, and the opportunities to reduce the upfront costs from the rebates to the smart payments to the alternative energy credit multiplier. You see, you get down to fairly low hurdle rate, or in terms of the upfront net costs for installing solar for these systems. And so when you pair that math with when you look at that math with the cost over 20 years of purchasing them and running them, you run into, again, very, very compelling economics for matching PV with air source heat pumps. I hit on it a little bit earlier, but and Dana's obviously going to get into it a lot more, but the issue of designing systems and obviously installing systems is really important. A couple of years ago, we worked with DOE to put together some guidance, realizing that this was an issue with how to design and size systems. And one of the other tools that we've made available as part of our cold climate air source heat pump product list is really a lot more information about the system's performance, not only at low temperatures, but across the heating and the cooling season. And so I think the bottom line here is that we really do need to change the way that we select and design systems. A lot of the old rules of thumb really don't apply to this new technology. So the message is that you really need to know more information about the system's performance than just simply its heating seasonal performance, seasonal cooling performance. its heating performance at 47 degrees. While helpful, you really need a lot more information than that. And so the message is that both on the NEAT product list that's publicly available, we've collected the extended performance tables essentially and put them in a consistent format. That's not to say that a lot of the technical manuals that manufacturers provide that information as well. So you can look in their tables as well and look at different temperatures and the ability to deliver capacity and efficiency. So yeah, again, the message is when designing and sizing these systems, you need more information than I think what was probably used in the past to size and design. All right, so that is my that's the first half of this hopefully awesome presentation, and I'm going to hand it over to Dana.
Thanks, Dave. Thanks for the kickoff. That's great. Yeah, so and I guess I'll try and hang out over here a little bit close to the mic, but I think when people have this conversation about heat pumps, there's different stages of sort of recognition and absorption of the information about it. There's sort of this, oh my goodness, have you heard about heat pumps? There's this new thing that's come and arrived, and people are, I don't know anything about it, but I hear good things and people like that it's more comfortable. Oh, good. Oh man, this will allow me to do a mic drop at the end too. That's great. Okay, so a lot of times, there's a lot of excitement early on, and then we, have evaluators go out and they look at what's actually installed and how it's actually operating, and then they say, oh, well, this didn't work so well, and that didn't work so well, and, it's kind of like a hammer. It's very, very useful, but if you get reports of people breaking their thumbs, you're like, well, should we be using hammers? Well, of course, you just need to know how to use the tools properly. And so that's really where, this kind of a form is so powerful, because they can be used, if they're used properly and installed in the correct manner, and it's really not that complicated to figure out how to do it, they work fantastically well and can save a lot of energy and reduce home heating costs for people, make them more comfortable in their homes year-round, and reduce carbon at the same time. It can deliver all of those promises. So factors associated with sizing that people talk about, this is sort of the comparison between fossil fuel-fired systems and air source heat pumps. With the conventional fossil fuel systems, HVAC guys have been oversizing systems forever. They've been going into a house. They don't necessarily do a manual J, or they haven't necessarily done, the load calculations. And they're like, well, this looks like a 100,000 BTU boiler home, or 150, or, whatever they're used to installing, they'd put in these systems. And so if you had a home that had a lower load, like a 60,000 BTU load at design, and they put in a 120,000 BTU unit, what that ultimately means is that on the coldest day of the year, the design temperature, that boiler is going to run for half an hour out of the hour. Turns on, runs for a few minutes, shuts off, turns on, shuts off. So you see all that cycling. From an energy perspective with a fossil fuel system, you get lower efficiency by having all of that cycling, because it doesn't really get a chance to get to its promised efficiency before it has to shut back off. And so it cycles on and off. But the consumers, outside of having a higher fuel bill, really didn't have any difference, unless it was super extreme situations, didn't have a lot of difference in that comfort. Most of the time, and I think that, I don't know, maybe somebody would object to this, but, most of our season is not at those extreme temperatures. Most of our season in New England is in the 20s and 30s. At least during the day, and then might get a little bit cooler at night. And so in that prior example of a conventional fuel system where it's oversized by 2 to design temperature, now, like on an average day, it might run 15 minutes out of an hour or 10 minutes out of an hour in 3-minute spurts, right? So that's where we get to, right sizing conventional systems is important. Well, we have the same phenomenon with air source heat pumps. And the reasoning behind it for HVAC technicians is similar. They don't want callbacks. They don't want anybody calling them and saying that they didn't get enough heat or they were cold. And so they're inclined to oversize these systems and write it off and say, well, They're variable speed. They can scroll down, no problem. Don't worry about it. It's all good. But there are consequences of having a system horribly oversized, dramatically oversized. And so that's one psychological driving factor for the HVAC technicians. The other part of it is the HVAC sales guys when they walk into a home and they talk to consumers and they say, hey, we're happy to sell you a heat pump. You know, where do you want to heat? Which rooms do you want to heat? Well, the consumer says, I want to heat all my rooms. I want all my rooms to be comfortable. Well, okay, we'll put a head in this room. We'll put a head. You saw the example from earlier slides. We'll put one in any zone in each one of these different rooms. Oh, well, okay, if we're going to have that many zones, then we obviously need to have a large outdoor unit that can accommodate all of those heads. And so then we're into a large size unit that's likely significantly larger than it needs to be. But so that's where the conflict is. And that's where the design problem comes into play and everybody gets concerned about it. And really the answer is you can give the people whatever they want, even if it's not entirely rational. You just have to break up the outdoor units into smaller outdoor units to match the load. That's the conclusion. We'll go through the different slides, but we'll come back to that again. So here it is. Trying to condition too much space. Here's an example of somebody who's putting in a one-to-one unit in an entire house. I know what this is all about. This is how I heat my house for the last 5 years. And what happens in this situation when somebody puts a one-to-one unit in, they get a very high efficient unit. It runs really hard, but you're going to get a temperature difference between the living room area and the bedrooms. In my house, I have a small house with a small heat pump, and from where the heat pump is to the far corner of the kitchen might be 35 feet. And so in the dead of winter, I have my heat pump cranked up really high to try and provide enough heat throughout the entire house. But I'm still going to have a 4 or 5 degree delta between those spaces 35 feet away. And for me, and I live in Maine, and we're all rusty, so it's no big deal. And the bedrooms are a little bit cooler, but we kind of like cooler bedrooms, kind of, in the winter. It totally depends on your preference. So for us, it's totally cool. It's awesome. It's great. High performance, low energy costs, some differential in temperatures, but not for everybody. And so it really depends on, the clients and what their desires are in a system. And so a lot of clients might gravitate towards something where they have heat pumps or want to have heat pumps and control in every single room. And I can't blame them for that. That's a lifestyle choice, and it certainly doesn't hurt sales. But it's more than they need. And if you were to take a small home, and this is one of those things that we'll cover in like the case studies class, you took a small home and you put 4 units on a large outdoor 4C36 that does 45,000 BTUs of heat at 5 degrees Fahrenheit, it might be double the amount of heat that they need. And the level that outdoor unit can scroll down to might be close to what their design temperature is. So that, when it's really, really stupid cold. So when it's at regular temperatures in the 20s and 30s, it's going to be less than the large outdoor unit that can support 4 heads would want to operate on, so it's going to cycle on and off, and you get the same poor performance problems and comfort problems that you would have if you oversized a conventional fuel system. So how do we get both? Well, there's a couple of different strategies. One of the strategies is to really go high efficiency. And of course, we're talking about smaller, tighter construction. This is all, new construction. So this is really, a completely appropriate pathways to reduce the number of zones in the house. You can see here they placed a wall mount unit in the living room and a small ducted unit that serves both the bedrooms. And that could be positioned on 2 single zone systems, which would give them a higher level of efficiency and also give them better scrolling up and down throughout the entire seasons. Or you could put it on a small multi and just say, well, I'm going to put 2 9,000 BTU units or 12,000 BTU units and attach them to a small multi that can do 20 or 24,000 BTUs as its peak. And that would be totally satisfactory. Of course, unless you put in a damper system or something, you would have one thermostat for both bedrooms. So occupants would have to agree on what temperature they wanted those bedrooms to be at, but that's perfectly fine. The other alternative that isn't on a slide on this would be to say, well, maybe I end up having the bedrooms on a small multi and I just have the core of the space on a single zone system, and knowing darn well that, like, for all intents and purposes, that single is going to provide 80–90% of all the space heating and cooling that they really need, and it's only in extreme temperatures that they're really going to rely on the bedroom units at all. And so if they have that extra unit, it provides some redundancy and safety, but it's really not a terrible negative on their overall energy consumption and efficiency. Okay. And so this really gets to the trend that we're seeing around new construction. Code has changed. Code continues to change, and houses are getting much tighter, and there's a requirement for ventilation and for tightness levels, and that reduces the overall heating and cooling load. So here's an example, a pretty traditional house. It would be very common for a code-built house to have a design load in Massachusetts. Our design load temperature here in this neck of the woods is, in the low single digits, 50,000 BTUs. Just to kind of translate that for people, how many people know how much oil they use during the course of the year? Well, I guess I should ask the question, how many people use oil to heat their home, right? I mean, Massachusetts is something still like 40–50% oil, and some fraction of natural gas. Maine, only about 7% of the homes have access to natural gas. We're still at like 70% heating oil. So it's a little bit of a different dynamic. We also have lower electric costs, which plays into some of the economics. But a home that's has a peak of 50,000 BTUs, if it was on oil, is something like 700 gallons of oil equivalent over the course of the entire season, right? Or maybe like 900 gallons of propane kind of thing. And so that same size house built to the code that's anticipated for next year at design load will be 20,000 BTUs. That's more, now that same home, the same looking home, is just tighter and better insulated. That's going to be more like 300 gallons of oil. That's the kind of efficiency gains that we've seen. And so that means less mechanical equipment in order to accommodate for heating and cooling, smaller sizing. So the way that you determine load calculations, and there's many energy modeling softwares out there for different purposes. Energy auditors use different ones than folks trying to calculate loads. So when you get an energy audit and they use TREAT or REM rate or some of these other things to determine what your savings would be for different improvements, they're really using the same physical properties of measuring heat loss in a house, conduction, convection, in order to determine what the load is. And so the standard is this manual J, which looks at all those factors, and you enter them into the software and it pops out a number. And so just like every other piece of software, it's horribly inaccurate unless you are very, very careful with the variables that you enter. So if you give the same software to 10 people and they make different assumptions, they can come out with 10 different answers. And so it should serve as, and it's an important tool for making sure that you set up the systems properly, but it should be viewed with some back checking. Like when I always encourage anybody that's doing their manual J, once they come out with their figure and they say, oh, 50,000 BTUs, to just step back and say, okay, does this look like a home that's going to use 700 gallons of oil? Just to kind of like look at it from a level of sensibility, because if they fail to take into account how tight the house is, or even, the position relative to the sun, turning the house 90 degrees, depending on the amount of windows in it, can make a difference of 12,000 BTUs in your design load pretty easily. So position, there's an air leakage, there's a lot of different factors that go into determining what the load is, and and manual J can be a very powerful tool for that, as long as people are being true to the leakage rates and the actual insulation levels. I don't want to frighten anybody off of using sizing software because you absolutely should, but it's not a magic bullet. Okay, so the next couple of slides really talk to the implications of the different sizing and how they match up with different systems. So here's a house, like we're talking about Worcester, right? So, you know, the actual, and this is the design, the temperatures of the house. So the temperatures that we experience during the winter, you know, on average. So you can see when we get down into December, January, there's often a period of time where we're down in the single digits. And, you know, sometimes it spikes down a little bit lower for an hour or two, but, you know, that's about it. It's not very frequent. And so over on this side, this is a home that, you know, somewhere in the middle there between 10 and 0, you know, you can imagine it would be 26,000 BTUs. So that would be the design heating load, 26,000 BTUs at the design temperature for central Massachusetts. And, you know, so people would size it to that kind of a system. Now, if you take a 2-ton system, and it doesn't matter whether it's Mitsubishi or another manufacturer, if it's a cold climate unit that can provide that, you know, 24,000 BTUs of heat temperature at around 0 degrees, that's the sort of the maximum. That bottom line is the maximum amount of heating that it can provide and cover everything. So even on the coldest day, you're matching it, and the HVAC guy is all happy. He's like, oh, I've matched the bottom load. I've got it all covered. But you can see that, like, when it's above 40 degrees, that's the lowest. What's being represented by that top end of that rectangle is the lowest speed the heat pump wants to do. And there's many different ways of representing this graphically, but this is a nice example because you can see the impact over the season. So, you know, when you're, you know, now October 1st until you get to November, there's going to be a number of days where the unit cycles. Now, this is a 2-ton system. If you had a 3-ton system, you can see, oh my goodness, it's going to be flashing on and on, off all the time for this relatively low load home or a relatively small, relatively decent construction home. So here, right, so there it is, 3-ton home. Oh, it's too much. And like, so if we had put in the 4 zones and the 4 little bedrooms, that unit's going to be cycling on all the time and causing high electric bills. And when I say high electric bills, like, I have a small heat pump in a small house that's old, but I've tightened up and improved the insulation. It's not anywhere near like a passive house or anything like that, but it does have contiguous foam insulation on the exterior. My total heating cost in Portland, Maine is about $500. And I've seen homes that are similar in what they should be for a load, where their monthly cost is $500 because in the middle of the winter, because they have all of this tremendous fluctuation and their system is oversized. So that's like oh my gosh, that's you know, the grand scope of terrible things that could happen. And then here is matching it with a 1-ton system, right? So 12,000. This is more like, I guess this would probably be more like my house. My house is probably a little bit lower load than this one, but like I said, it's small. And you can see that, like, oh my gosh, you know, for most of the season until you get down into the mid-30s, it totally takes care of everything. But once you get below the mid-30s, that's when you'd want to have some additional supplement to keep you comfortable, or you'll get more, you know, temperature variation throughout the structure. The alternative to that is to put in 2 single zones. So now you get all the variability of a single zone that's going to take care of the main central living space, but also have enough oomph between the 2 of them to cover all, including your extreme events. So that's where we kind of, you know, remember we were looking at the alternative of having a single zone in the living space and then having 1 small ducted that goes to the 2 bedrooms. That's this, 2 12,000 BTU units that can operate to low temperatures, gives you great comfort and great efficiency, right? That's not that complicated. Example, you know, again, this is the warmer seasons, right? The other chart was October until March. This is kind of getting into your cooling season. You don't really need cooling until you're, you know, maybe, I don't know, 75, 80 degrees outside at least, right? And even then the cooling load is pretty low. So if you would put that 2-ton multi-zone system in, that would, you know, cycle a little bit in the fall for heating, but more or less cover everything the rest of the season a little bit oversized. You can see that it's dramatically oversized for the cooling load, right? So the consequence here with a 2-ton system in this relatively low load home is you're going to have cycling all summer long. It's not nearly as big a deal in New England as it is, cycling for the heating, just because we have so much less need for cooling. I mean, it's just a tiny fraction of the energy and cooling load or whatever. So it's like, if you end up having some cycling as a result of cooling, it's not nearly the energy penalty that you would by having it oversized for heating. Here again, an example of 2 1-ton single zone. So that's just one single zone shown, right? And it's going to take care of pretty much all your cooling throughout the season. So remember how we had the 2 units broken up? So you can have 2 systems and you'd only operate one, right? Or you could, you'd have plenty of cooling load, but you could do it in the space. So here again, we're really pointing out that multiple single zones can be highly effective in both matching the load and providing higher efficiency. Okay. There are a number of folks that have done studies on the impact of efficiency by the different designs. And I don't know how many folks were in the last one talking about coefficient of performance, COP, but the COP is the number of units of energy, of heat energy that you get out for every 1 unit of electrical energy that you put in. So heat pumps are awesome because you can get 3, these cold climate units can reliably provide on a seasonal basis 3 units of heating or cooling energy for 1 unit of electricity put into them. But if they're cycling a lot, there are cases where a home that, is just dramatically oversized, over the course of the entire season, you might only get 2 units of heat out of it versus 1. Still, it's not, it's twice as good as electric resistance, just not as good as it possibly could be. Oh, and these last 2 bullets are kind of important too. When a system is cycling, it's not providing heat. When it's not providing heat or cooling, now that's when you get your temperature fluctuations, right? So you end up with less comfort and higher electric bills. When you're doing new construction, it's important to take into consideration, where you're going with the installation, what the tightness levels of the home are, and what the end user is going to want in the home. Where you want a placement of the units, which style of wall thermostat you're going to install. I'd highly recommend in new construction using wall thermostats. It improves controllability no matter who ends up living there. You need to make sure that you're working with the plumbers and the electricians to make sure that you have, the electrical lines, the proper kind of wiring run to the locations. Most of the single zone systems use, 14 gauge stranded wire. All the HVAC plumbing distributors carry the wire and can talk to the electricians to make sure they understand it. It's becoming more and more common, so people generally know what the materials are. One of the code requirements in the middle of these bullets here is having a 110 volt outlet nearby. I think the code is within 25 feet to allow for servicing. So, when somebody's servicing the unit, they're running a vacuum pump or they're using, some other piece of electrical equipment or lighting, they may need to have an electrical outlet there. Code requires that there's an electrical outlet in proximity to the outdoor unit. And of course, there's minimum distances from any flammable items, propane tanks or natural gas vent lines or that sort of thing. This is really kind of a relatively new concept, which is just a great idea. A lot of new construction uses these pre-built trusses that go across them, and relatively recently they've been coming out with these high-performance truss designs that includes this pet plenum, right? So you can see that they've basically built in a box that goes up, and that doesn't really disturb the structural integrity of the overall roof system, but it gives a really nice clean surface to insulate. So you insulate the inside of the box, and now everything that's inside of this box is part of the thermal envelope of the house, right? Anybody have a question on what the term thermal envelope is? I mean, if you're here, you probably have heard that term at least once or twice. Okay, so it's great to have, especially when you have ducted systems and you have these metal ducts, you really kind of want to have that. You're going to enhance your efficiency by probably 20% by having your mechanical system within the thermal envelope. And so if you're doing a new design and you're going to use a truss system, having a plenum built in and then, having your ductwork run along the hallway, through the core of the house and then just drop ducts into the different rooms is super slick. Yeah, and, and this is the case in a lot of new construction where we're doing slabs. People are moving away from having full basements. And so, working your mechanical system or being able to put your mechanical system into a closet is a big construction advantage. Design considerations, whether it's one or multiple outdoor units. I would recommend that if you use brackets for mounting the outdoor unit to the side of the building, that you use a bracket that actually kind of comes along and then has another little jog and lags into the concrete of the as opposed to the wall of the outside of the house. My unit is mounted to the side of my house in the middle of the winter when it scrolls up to full speed. I can hear it. It's not nearly as loud as the old lifter pump used to be, but I can hear it. And so clients are going to have different levels of sensitivity to the noise that it can make. And it depends on the structure of the building. If it's, in the middle of a large span and it's just a 2x4 or 2x6 construction, you can get to this harmonic where you'll hear it. So you might as well just put it on a stand and separate it off or have it lag to the concrete and then noise is never an issue. Other placement considerations, it's, in Maine the standard is to have it at least 18 inches off of the ground and to instruct the clients to make sure it stays clear of snow. If you have a snow drift in the system, it's going to be a problem. By being 18 inches off of the ground, during the winter when it goes into defrost mode, it melts any snow or ice, and that's an automatic feature of all these systems. It melts any, it's the middle of a blizzard. There's lots of snow in the air. All that snow gets caught on the radiator on the outside unit, the coil on the outside unit as the air flows through it. So it has to go through periodic defrost. And when it goes into defrost, it reverses its cycle, draws a tiny amount of heat in from the house to the outdoor unit, melts all that snow off of it, pours down into the base pan and drops down below the unit and forms a glacier. And if that glacier has, some growing room, it's fine. It's no problem. It's, just happy little glacier. Nobody ever thinks about it. But if the unit is parked on the ground or just 4 inches off of the ground, that glacier grows taller than that in some weather conditions and will get up into the unit and cause damage to the coil and break down the system. So that's why and it's really, I think it's a reasonable standard for even Massachusetts, but it's the case in Maine that every unit that gets a rebate has to be 18 inches off of the ground. Also mentioned is not being under a drip edge. If you have bulk moisture pouring onto the unit and splashing on the top of the flat roof, it goes over the top and the front and the back, and you're going to go into defrost cycle more frequently. There are caps that most distributors carry that will divert the airflow and splash it forward in front of where the air is blowing out. I'd recommend those in all circumstances where the unit has to be positioned underneath the drip edge. Okay, so I think these are reasonable suggestions for how you think about heat pumps when you're designing a home or any sort of residential or commercial structure, frankly. Like we started out with, people are excited about heat pumps, and then there's an introduction of this idea that there's a lot of complexity to make sure you don't screw up, and really it just comes down to understanding what the load of your building is and matching the load with the different kinds of systems in order to accommodate the expectations of the consumers, the homeowners. And oftentimes that can be accomplished with single zone equipment. Multi-zones are awesome. If you have an office structure that has 8 offices and they're all going to be using heating load at roughly the same level, a single outdoor unit that can handle 8 zones for that kind of circumstance is awesome. Just really perfect. Great efficiency, just just right. But putting a super large system into a small house for relatively low loads in little bedrooms is not right. And that's where you want to look at having either very small multis or singles to provide those solutions. One of the other things that's been touched on a couple of times I just want to hit on is this point around balance point, and it kind of gets to some of the rebates right now in Massachusetts. The $1,600 per ton rebate associated with integrated controls has a switchover temperature at the economic balance, or at a balance point around 35 degrees. And I think part of the reasoning behind that is to mitigate any increase in the frequency that somebody might have frozen pipes in their house or something like that. I can tell you that, and I managed the rebate program in Maine for 7 years. We have 40, 50,000 homes with heat pumps in them, and there's no evidence that there's any increase in the incidence of frozen pipes. So I'm not sure that I can understand the conservative nature and the caution, but the consequence of having heat pumps in Massachusetts switch over at 35 degrees or 40 degrees is that you're only going to be covering a tiny fraction of the heating season. You're only going to reduce it maybe 20% of your carbon emissions by having that high of a turnover temperature. And I understand that the balance point, given the economic balance point, given the price of electricity in Massachusetts, versus oil might be 9 degrees or something in that ballpark, or slightly warmer if it's natural gas. The cost differential for using a heat pump to lower temperatures is not significant. If you were to ignore the balance point and go through the entire season using heat pumps, the cost penalty to the consumer is probably 10 or 15% total. But the carbon emission difference is dramatic. So that's my little pitch that I just wanted to squeak in on this, is that heat pumps work at very low temperatures. They work in northern Maine and have been successfully used to dramatically lower our burden on oil. And the phenomenon in Maine, I mean, there's no place else in the country that's installing them with the same frequency per capita as Maine right now. I mean, there are like 1 million people, 1/5 of the number of people in Massachusetts, and we're on track to do 10,000 heat pumps in Maine this year. And of course, the governor intends to get to 100,000 in 4 years, and it's going to be quite a ride. But Massachusetts is just a couple years behind us on that curve. I fully expect that 50% of the homes in New England will have heat pumps within the next 10 years. It's going to be a dramatic shift. And this is really what we're experiencing is the greatest shift in heating technology in the Northeast since we transitioned from coal to oil. And so sharing this knowledge and getting everybody up to speed as quickly as possible is really super powerful, and I'm really greatly appreciative of your attention today. So I do talk to architects and engineers with some frequency, but really my day job is training installers. And so all the manufacturers, Mitsubishi and Daikin and Fujitsu, we foster a whole network of installers and have them go through training and use our resources and understand. We have modeling software and all those other pieces. So. And we're trying to continue to grow that because we see where the marketplace is going, and we know that we need more technicians that are trained to do this work properly. And so the suggestion is find a contractor that's aligned with the manufacturer that has status with them, like a diamond contractor or elite status with Fujitsu or whatever it is, that has those credentials, because that means that they've received that level of training and that they have that rep on speed dial. My phone has rung like 3 or 4 times during the course of the last 45 minutes.
So you got a certification program for Mitsubishi?
That's right. Mitsubishi has a full training center in Southborough, and every week that training center is packed with people learning the basics of M&P or advanced controls or what have you. So, and Mitsubishi has a tremendous amount of resources online that can be accessed by anybody. At mylinkdrive.com. Yeah. So I did bring both the M&P manuals. I'd encourage you to pick up one of those. But that website that I mentioned, mylinkdrive.com, that is an incredible library of all of the install manuals, documentation, submittals for every single product that Mitsubishi has provided into the U.S. marketplace for the last decade plus. It also has videos, software that you can download directly, no passwords or anything. Yeah, great. So Jim's asking about just some brief comparisons between air source heat pumps and ground source heat pumps. So obviously I have some bias, right? But I did manage the rebate program in Maine that covered all heating systems, weatherization, air source heat pumps, as well as geothermal. And, so that was about 2 years ago when I left. And so in the period of 2013 to 2015, we really kind of had a big surge in geothermal. Efficiency Maine was offering an incentive of $5,000 in addition to the 30% tax credit from the federal government. And of course, sitting in that seat, I was seeing all the data coming in from all these projects, including their average install costs. And geothermal, if it's, it's no small project. Depending on what you're trying to do, you either have to, put in coils, which involves a lot of excavation work, or do drilling work. And earthwork is very expensive. And so in Maine, for the hundreds of projects that got processed during that period of time, the average install cost was high 40s. It was close to $50,000 as an average initial cost. So if you got $5,000 off of a $50,000 project and you got another 30%, $15,000, $16,000, well, now you're in the mid $20,000 range, and you might get some, maybe 10% efficiency annual savings over air source heat pumps over the course of the life of the system. So if $50,000 upfront cost was not a barrier to you, and you could wait 20 years to get your payback, geothermal's great. It depends on the economics. I mean, people would come up to me and say, well, I used freshwater wells, and I already had the well, and so the total install cost was $20,000, and I got 30% tax credit and whatever. And so there are examples where it's significantly less. Yeah. Yeah, the incentives make a big difference, but absolutely. I mean, it's great technology, but it's been around for a very long period of time. And I think part of the cost is appropriate. I mean, like making sure that that system is done properly is key. So ASHRAE has those standards for every temperature for both the heating and cooling design temperature. And like for both the heating and cooling side, when you look at that temperature and you plug in the variables into the manual J calculation, it has a fudge factor in there to accommodate, those seasonal fluctuations to variation. And I mean, like, it's conservative already. So manual J is just really the first chapter. There's actually a manual S and a manual, for selecting the equipment. And that has a bunch of different guidance, and we kind of get into that in some of the later slide decks. But you're not supposed to size the cooling equipment greater than 130% of whatever comes out of your manual J. And there's also rules about like matching your cooling to your heating load that come with manual S. So I know that, and then there's a manual D for sizing your ductwork. Oh, I'm getting 5 minutes. I'm hopefully going to get out of here sooner than that. But so those different, I would look into those different strategies and look at the design temperatures for the buildings, and it'll come up.
These are actual temperatures from that year, right?
Correct.
So that's the actual, all the fluctuations you see is the real weather data from Worcester over that year period.
Oh yeah, so it's 2019, 2020. I always use 30-year data, but that's great. Ideally, it's running all the time. Ideally, you're just sitting there and you're idle. Like, the ideal circumstance is that, when the beginning of heating season starts, when it's 60 degrees or below outside, 55 degrees, and you need a little bit of heat just to keep the place warm, that you're kind of idling along at the lowest level that the heat pump can do, and it's just continuing to operate at 20% or 25% of its operating capacity. And then when you get to the peak of the season, it's running at 100%. And it's fine. I mean, like I have my system is actually undersized, right? When it's really extreme temperatures, I need a little extra boost of heat. I probably need to put in another one or a little bit bigger one, but I have it cranked all the way. I have it I set my thermostat on that unit at like 78 degrees and just let it ride, and it maintains 68, 70 degrees throughout most of the house. Yep. Well, so that's a variable, and you can adjust. But I think the standard is 65 degrees for your indoor temperature, and then it assumes what your design temperature is, and there are design temperatures associated with every weather station in the country. 68 degrees, and so I think you're right. Yep. Right, or 72 for cooling. But there are, and when they pick that design temperature, it's representative of something like the 97 or 98th percentile of coldest days. So it's not saying, it was never, it's not, the idea behind the design temperature is not to say, well, one day it was negative 20 degrees here, so I need to size the system for negative 20, because when you, and it's not part of this slide deck, but 2 years ago, the polar vortex came swirling through here, and it was really, really cold, and everybody was like, oh my gosh, it was negative 20 for 2 weeks straight. Well, if you go back and you look at the weather data, maybe the wind chill was negative 20, maybe the load on your house was at that level, but it was really only in Bangor, Maine, it hit negative 20 for a half hour during that 2-week period in Bangor. So, I mean, like, our perceptions of what, constitutes super cold weather and what actually happens is a little bit different. And so the design temperatures have a whole layer of fudge factor built into them to accommodate for those extreme events. And so by choosing a design temperature lower than in the actual location, you're automatically walking towards oversizing. But his follow-up question was regarding the efficiency of multi-zone systems. And you can, HSPF, the heating seasonal performance factor, is not a perfect test. There's a lot of things about that test and the way that it does the efficiency that are just kind of squirrely. But one of the things that you should know about it is that it gauges the performance over the season for a zone between northern Virginia and southern Massachusetts. So it's like, it doesn't really translate perfectly to northern climes, or, even in Massachusetts is kind of the northern end of that. But it is a metric. And so all the different heating systems that get tested against that, you can look at their efficiencies and gauge them. And if you look at single zone systems, it's very easy to find, and in fact the standard in Maine is to have HSPF 12 as a minimum to receive a rebate. There are many heat pumps that hit HSPF 12 as singles, but multi-zones, only the highest performing ones are above 10. There are some multi-zone circumstances where you can get to 11, and I got 2 minutes, but you can see that comparison. And part of it has to do with the way that they're tested in terms of their efficiency, because they require that one of the indoor heads is shut off during the course of that test exam. But the other part of it is, like, if you have a 3-zone that's hooked up to like a 24,000 BTU unit that's attached to 3 9,000s and only one 9,000 is calling, you have a 9,000 coil on the inside calling a 24,000. There's a mismatch in that sizing. So the frequency that you have a mismatch between the indoor and outdoor coil size and the compressor contributes to a slightly lower efficiency than you would with a 1-to-1. And there's some other factors, but they don't fit in 2 minutes. I'd be happy to chat about them later. Thank you so much. Great session. So.